Okay, let's get started. So as we said, today we are going to talk about quantum Fourier transform. And so any question from this time? This time we have a very rough overview of discrete Fourier transform, which is going to be generalized into quantum Fourier transform today. Okay. And anyway, discrete Fourier transform is a very useful conception or transformation in all kinds of engineering and I guess scientific study. Okay? It tells us how you get different, I guess, vibration, oscillating component of the real signal to, yeah, I guess mathematically it's a linear transform, so it's a matrix that you can multiply on an n-dimensional vector to get another n-dimensional vector. And in engineering, it lets you get all the different frequency components of your signal. So if your so you think this discrete signal is oscillating at a higher speed, then you will Fourier transform to a signal that has a higher value. So if you have a constant signal, you will Fourier transform to 1. If a signal with this frequency 1 or 2 pi, then you Fourier transform, say you have frequency 1, and you have higher frequency, then you will say you Fourier transform to higher frequency. Of signal says that you have higher frequency, etc. Okay, but well, we just need to know it's very useful for signal analysis. But now we want to talk about quantum computing. So Fourier transform is traditionally already a very useful thing, and we want the quantum version of it. And it's a quantum Fourier transform, and kind of like how we hinted, quantum Fourier transform is basically just a discrete Fourier transform, but with the input and output being quantum state. Okay, so we think quantum Fourier transform is just a linear operator acting on orthogonal basis. This once again now it's n-dimensional quantum space, so you have this basis vector being computational basis 0 to n-1, and then the quantum Fourier transform has this same matrix element as the discrete Fourier transform. And let's see if I can click. No, I cannot. And yeah, so it has that basically. So this is now is a quantum matrix, and if you sandwich between k and j, this is basically the kjth element. Then it's kjth element of this quantum Fourier transform matrix is this 1 over square root n e to a 2 pi jk over n. Okay, and I think I can click if I do this. Okay, and yeah, wait. Okay, works. Okay, yeah, so you see that this is the same matrix element as before, so the kjth element of this matrix is this 1 over square root n e to 2 pi jk over n. And we also say if we have a vector of x to get transformed to a vector of y, then each coefficient yk here will be this 1 over square root n summation j xj e to a 2 pi jk over n. This is just you do matrix multiplication on this thing, and then you generalize that exactly to this equation. So we see that the jth element, the computational basis is j. So this is basically a vector with only xj equal to 1. So if you only have xj equal to 1, then then each yk will be e to the 2 pi jk over 1 over square root n. Okay, so you see that each yk is this 1 over square root n e to a 2 pi jk over n, and then there are all possible k. So then there are all possible k. So this computational basis j is going to be transformed into this summation k e to a 2 pi jk over n, and normalized by 1 over square root n. Yeah, so these two definitions of Fourier transform, they are equivalent, and they are just we generalize the I guess not quite generalize. We change the discrete Fourier transform to have the vector here being quantum state. So now we think those two vectors are quantum state. And now quantum Fourier transform is going to transform an input state to an output state. Okay, and yeah, okay. And yeah, so more generally, if we have this equation, then yeah, just like the xy equation, we can also write that you have a vector that x being input is with input with this coefficient hj, and change to output with coefficient yk. Then yk will be equal to the summation 1/n summation j from 0 to n-1 hj e to 2 pi jk, sorry, 2 pi jk over n, and yeah. And I think this equation is exactly this equation here. Yeah, this yk equation, same as this yk equation. So you see the relationship between yk and xj is exactly the same between the quantum Fourier transform and the discrete Fourier transform. Okay, and then one thing extra. So the matrix is the same, but now there is one more property that's more important in quantum computation. Is that we found that this f sub n matrix is also unitary. Okay? Unitary means that f sub n times f sub n dagger equal to identity. So let's write down the definition of unitary again. Unitary, f sub n being unitary means f sub n times f sub n dagger equal to identity matrix, obviously for 1. Okay, and this is important to be a unitary because we want that when you apply quantum Fourier transform on input state with a normalized input state, so it's a very quantum state, then you also have a normalized output state. Okay, if this is true, then quantum Fourier transform is a very quantum operation, and then we want to construct a quantum circuit to do this quantum Fourier transform. Okay. So there is also actually a quantum circuit to do quantum Fourier transform, and we are going to see that the circuit is actually very efficient, more efficient than classical Fourier transform in some sense. Okay, so people understand what's quantum Fourier transform. It's basically it's basically this matrix, this unitary matrix Fn. Okay, so and then even later we are going to see that this Fn. This Fn unitary is very useful because it's going to let us do vectoring efficiently. Okay, and now we start to go into how to construct the circuit for quantum Fourier transform efficiently. But first we need to set up some notation to make our derivation easier. Okay, so the first thing we do is we take big N equal to 2 to n. So so it's easier to express everything as qubits. Okay, so this big N is this is big N here. Okay, so yeah, because we are going to express everything binary, so we assume big N is 2 to n. And if it's not 2 to n, then maybe you can yeah, that's not going to do that. Let's just assume big N equal to 2 to n, and also and now because big N equal to 2 to n, then we are going to express our numbers as bit strings. Okay, so bit strings in this 0, 1 to 0, 1 to small n. Okay, so yeah, this is the obvious mapping between 0, 1 to the n and 0 and 0 to n-1. Okay, and yeah, so it's like this. So it's just like this. So you just write down things in binary. So if j is some number between 0 to n-1, then we can associate it with a bit string. That's this j1 to jn. So each j1, j2, j3 to jn is something between 0, 1. Okay, and then we think these are the binary strings. So if we have some j1 to jn binary string, then it corresponding to yeah, just things in binary, j1 times 2 to n-1 plus j2 to 2 to n-2 all the way to plus jn to 2 to 0. So for example, so you have this binary 1, 1, 0, then will equal to this 1 on 2 to 2 squared plus 1 on 2 to the 1s. So in decimal is 6. Okay, so this is basic binary notation. Okay. These people should. Okay. So we will say we will write this 0.j1, j2, j3, to Jn, and if we have this in binary, then hey, anyway, yeah, and if we have this thing, and then we actually means that this is a fraction, okay, and so this is just a binary notation for a fraction. So this it's j1 times 2 to the minus 1 plus j2 times 2 to the minus 2 plus all the way to jn. We have a typo here, so it should be I guess we have jm here, so it should be jm times 2 to the minus n. Okay, so this is a fraction. So for example, you have 0.11, and if this is a binary notation, then it's 2 to the minus 1 plus 2 to the minus 2. Okay, and so in decimal, that's 0.75. And I guess then, yeah, so any question? So this is just writing down boundary numbers. And we'll get lazy and we'll omit the sub B if it's clear on the following. Okay. Okay. Any question? Yeah, we'll actually omit the subscript B. Okay. And if that's okay, then we go to our actually important theorem to construct our circuit for quantum Fourier transform. That is, if we have input computational basis state represented by this bitwise notation, bitstring notation. So if you do quantum Fourier transform on this J1, J2 to Jn, and then it becomes this actually very interesting tensor product of different qubits. So you have a global coefficient 1 over square root 2 to n, and then each qubit is going to become tensor product of each other, and it's actually going to be we have multiple, sorry. So this one here, and there's one here, and there's one here. So each qubit is going to be kind of like 0 plus 1, but with different coefficient on the 1. Okay? And so first qubit is going to be 0 plus. Okay, so first qubit is going to be 0 plus e to the 2 pi I 0.jn1, and the second qubit is going to become e to the 2 pi 0.jn minus 1 jn1 all the way to the next qubit being e to the 2 pi 0.j1 j2 to jn1. And then remember, so this is 0.jn notation here. This thing was why we want to talk about binary. Okay, so this 0.jn is either 0 or 0.5 because it's this notation. This is 2 to the minus 1 times jn, so it's either, so this thing is all basically jn over 2. Okay, so this is jn over 2. Okay, and then this is jn minus 1 times jn minus 1 jn over 4, etc. Okay, and so you have those fractional, I guess not, fractions of minus 1 here, fractions of 1 here, yeah. Anyway, so you have those faces on 1, and so the claim here is that quantum Fourier transform, it actually do this thing. So so remember we are saying this quantum Fourier transform with coefficient e to the 2 pi jk over n. If you apply it on qubit string, then it actually has this funny expression. Okay, and then later we are going to see that this interesting expression is going to lead us to a very efficient quantum circuit to do quantum Fourier transform. Okay, and so let's prove the quantum Fourier transform. And so here we have a notation that has this just a zero tensor product here. Okay, so we have this big O times notation to mean that we tensor product a whole bunch of things together. Okay, and so we start doing our quantum Fourier transform by definition. So if we start with some j, then just the definition write down is this summation k, and so some normalization factor, then you have summation k and the kk, and with coefficient being e to the 2 pi jk over big N, and now big N is 2 to n. Okay, so yeah, and I guess we want to check the k part. Okay, and k over 2 to the n. Okay, and just as before, we say we have equivalence between a number. So here k is a number between 0 to big N minus 1. And then we use this equivalence. We want to identify a bit string with a number from 0 to n minus 1. Okay, so we change k to a bit string of k. So it's some big string from k1 to kn. Okay, and because k is from 0 to n minus 1, then also k1 to kn, each one of them is summation from 0 to 1. Okay, so the second step we did. Nothing much yet, so we change the summation from k to a big string, summation of big string k1 to kn in 0, 1 to the n. And also then we need to change the middle k part. So k was k was a number from 0 to n minus 1, and we want to express this number by the bit string k1 to kn. And then it's exactly this expression. So it's k1 times 2 to the n minus 1 plus k2 times 2 to the n minus 2 all the way to kn. Okay, and you write down a summation. Then you can introduce another dummy variable to make this shorter. So it's summation L from 1 to n, and KL times 2 to the minus L. We are also grouping this over 2 to n together. Okay, so the first one, because you divide everything by 2 to n, so j divided by, so this k divided 2 to n will be k1 times 2 to n minus 1 plus k2 times 2 to n minus 2, etc. Okay, so you have k1 times 2 to n minus 1 plus k2 times 2 to n minus 2, etc. Okay, so the second step, we only change the expression of k from a number to a bit string. Okay, and the next step, we write down this into tensor product of different registers. Okay, so obviously this k1 to kn is a tensor product of L of k1 tensor k2 all the way to tensor kn. Okay, so you can write this as this serial product L from 1 to n kl. And interesting thing is the coefficient also separate out to different kl, right? Because you have a summation of different kl on this exponent, then then on this exponent, then this summation of exponent equal to multiplication over the whole thing, the exponential. Okay, and yeah, so this summation KL can be changed into summation of different L can be changed into product of different L. So product of e to the 2 pi j, still the same thing, and the KL to the minus L. Okay, and yeah, so this is just breaking the summation into products, and then group them into tensors of different KL. Okay, and then we're actually almost done. Okay. And so we have these tensor products and the summations, and then we can pull the summation inside to the tensor product, because we see that, well, basically each KO is getting separated. Okay, and so you see that each component here so each KO is only inside its component, so we can pull the summation inside to each component of their respective KO. Okay, and so instead of summing summation K1 to Kn, then we just have each KO summation inside itself. Okay, yeah. Okay, so we can group the summation inside the KO. Just have each KO summing inside. So this is basically the distributive law of multiplication of tensor product. And then the next thing we do is basically we break out the summation. So KO can be either 0 or 1. So when KO equals 0, then here you have 0, and then the exponent is going to be 0 because yeah. It's going to be 0 because you have this 0 here, multiply everything, it becomes 0. And when KO equals to 1, obviously you have 1 here, and then you have e to a 2 pi j, and we should write excuse me, so we should not have KO here. E to 2 pi j. So excuse me, so let's mark out this KO, e to a 2 pi j times 2 to the minus L here. Okay, and then yeah, and then finally we got our result. So we just need to think about, okay, and have all the 1 here. And so we just need to think about what's this j times 2 to the minus L here. Okay, so j times 2 to the minus L is equal to j divided by 2 to L. J divided by 2 to L. And remember, this is j equal to j1, j2, to jn, and divide by 2 to L. Divide by 2 to L. So we can do a bit of a binary calculation, and that should be j1, j2, to j minus L minus L minus 1, and then we have the period dot here, and j minus L all the way to jm as well, and all the way to so jn. Okay, and I guess for example, if L equal to 1, then last thing is j1, j2 to so this thing, if L equal to 1, then that's j1, j2 to jn minus 1 dot jn. Okay, so maybe it's easier to see. So you have j1, j2 to jn divided by 2, then you are just shifting the period 1 one slot forward, and so you have j1, j2 to jn minus 1 dot jn. Okay, and but this thing is, oh, excuse me, and but if you e to a why am I missing this? But anyway, but you have e to a 2 pi j. Sorry, then you have e to a 2 pi j mod. So you have e to a 2 pi j on this thing, and but we know e to the 2 pi I times any any integer n, e to a 2 pi equal to 1. So e to the 2 pi to any integer number equal to 1. Okay, and so this is j1, j2 to jn minus 1 part don't matter, and so you only have e to a 2 pi, and so the only important part is e to a 2 pi times this 0.jn. Okay, because the integer part you have e to a 2 pi equal to 1, so e to a 2 pi times to any integer is just equal to 1. Okay, and then similarly for L equal to 2, then you will move this period forward 1 more, and you have j1, j2 to j2. You have j1, j2 to j2 j sub n minus 2 dot jn minus 1 and jn, and once again the integer part doesn't matter, and so you are just left with e to a 2 pi j, e to 2 pi 0.j minus 1 jn. And yeah, so with more you divide by larger and larger power of 2, and in the end you have L equal to n, and you just have this 0.j1, j2 to jn. Okay, So this is a bit of complicated calculation, but it's pretty straightforward mathematical calculation. People have questions? Okay. And if okay, so yeah, so this is kind of heavy calculation, but in the end, we prove that quantum Fourier transform is this thing. So J1, J2 to Jn is this 1 to 2 to 1 over 2 to n minus 2, 0 plus e to 2 pi 0 point j k to 1 times 0 plus e to 2 pi 0 point jn minus 1 jn 1 all the way to 0 plus e to 2 pi 0 point j1 j2 to jn 1. Okay. And if okay, then finally we can have our circuit. Okay. And so we kind of borrow the picture from Wikipedia. So here is our efficient circuit for quantum Fourier transform, and here we need to introduce a notation. So we have this R sub k rotation. So we need to do a lot of fine rotations because we have this very detailed phase here. Okay. So we are going to do a whole bunch of controlled RK, where RK is a rotation of very small phase. It's a rotation, yeah. So it is get where if the input state is 0, you do nothing, and the input state is 1, you rotate it by e to the 2 pi over 2 to the k phase. Okay. So this phase angle is going to get exponentially smaller with k. Okay. And anyway, so we can that this is a circuit for quantum Fourier transform. So you have the input qubit being listed here. So it's x1, x2 to xn, and I guess we should, or maybe this as j1 to jn, but doesn't matter. To fit with our notation. So I guess this is actually j1 to jn. So x1 is j1, j2 to jn. Okay. And what we do is we do this kind of thing. So we say first qubit we put Hedema, then control second qubit to rotate to control R2, and do R2, and control third qubit to R3 all the way to control nth qubit to Rn. And the second qubit is similar. You have Hedema, then control R2 all the way to control Rn. And minus 1 qubit you have Hedema, and control R2, and less qubit you only do Hedema. Okay, and we can the end result is this thing, and it's 1 by square root 2 0 plus e to the 2 pi 0 point so x1. So I guess here we're being lazy, so jn1. Okay, and you see that this is basically our the end result here the end result here was just our derivation here, but with the reverse order. So if you do this circuit and the reverse ordering of all the qubit here, then you have done quantum Fourier transform. Okay, and but that's claiming that this is true, and let's see a few details. Okay, and let's see a few details that why the circuit actually gives this output. And I guess we can just do qubit by qubit. So if we see what happened on first qubit, so let's first prove that the first qubit becomes this thing. And I think this is pretty obvious. So you start with x, and you do Hedema, and so you become you do Hedema, then the first qubit just become 1 by square root 2, and 0 plus 0 plus e to the 2 pi 0 point j11. Okay, and I guess here we can write a bit more. Okay, so if j1 equal to 1, then we have after Hedema is 0 plus 1. 1 by square root 2, 0 plus 1, and skipping the 1 by square root 2. And j1 is 0, then excuse me, I got it wrong. Okay, so remember so J1 is 0, then heading on 0 state you have the plus state, which is 0 plus 1. And J1 equal to 1, then you got a state that's 0 minus 1. Okay. And so 0 plus 1 equal to this thing, 0 plus e to the 2 pi times 0 times 1. And then 0 minus 1, we have this minus sign is equal to. So we have a very complicated way to write minus sign is e to the 2 pi I times 0.5 times 1. And that's because e to the pi I equal to 1. Okay, let's erase a little bit. E to the 2 pi, 0.5. Yeah, so that's you do Hedema. And so Hedema, put this x1 to this e to the 2 pi 0.j11. And then you do control R2 on the first qubit. Then you, so second qubit is J2. And so control on J2 being 0 to 1, you do either e to the 2 pi over 2 to the 2. And good thing. Yeah, sorry. And so control on R2, you will get the extra phase on the 1 bit on the 1 register. On the what should I say, on the 1 component of the first qubit, because that's RK2. RK says on the 0 component you do nothing, so 0 component still have no phase, and 1 component gets this extra phase of e to the 2 pi over 2 to the k, and so e to the 2 pi 2 to the k, so I guess I should write, you get the extra phase of e to the 2 pi I over 2 to the k, and if you write down in binary, then that's equal to e to the 2 pi I times 0.01. Okay, and then you have this, and you only apply this when J2 equal to 1. So that's actually, so you will control on J2. So you have control on J2. Then that's actually the phase you got is e to the 2 pi I 0.0J2. Okay, because only when J2 equal to 1 you have this phase, and the J2 equal to 0 you don't have this phase. Okay, and so hopefully I convince you that when you do control R2, you get this you get the extra e to the 2 pi 0.0J2 phase on your 1. Okay, and then you can see how this is going. Then you control on the third qubit to do R3. Then you get this extra 0.00J3 on your 0.0J3 on the phase here. Okay, and so if you control all the way from R2 to Rn, then your phase will become this e to the 2 pi 0.J1, J2 to Jn. Okay, and yeah, that's why the phase here is, that's why the first qubit, and then you see that after all those control, you do nothing on first qubit. Okay, and so the end result on the first qubit is this 0 plus e to the 2 pi 0.J1, J2 to Jn1. Okay, and then you still have the other qubit being the same because nothing written down on them, they have only been controlled. Okay, and so that's why you get the first qubit, and then similarly on second qubit, when you do Hedema, then you get this 0.J2, and then you do those control, then second qubit is control on the third qubit with R2, and then you get the extra 0. Excuse me, and then you get control on 3, then you get the extra 0.0J3 on it, and then you will control all the way to Rn, so you have the 0.J2 to Jn, etc. on the second qubit. Okay. And hopefully you see how the recursion goes, so you just fix up the qubit 1 by 1, and then with those Hedema controls, you get the correct phase on the 1 component, And so in the end, you are left with the last qubit will become 0 plus e to 2 pi 0.jn 0.jn here. Okay, and yeah. So any question? So yeah, so we do first qubit, second qubit, and we do all the qubit, and you see that this is very similar to what our quantum Fourier transform expression we have, and then we reverse order, then you see that we actually got what we had, and so we are forgetting the K1s here. K1, K1, and K1. K1, K1. Okay, and yeah, so this is what we get after doing Fourier transform. Okay, and if there is no question, then let's run a small example. Okay, so if we have a small equal to 3, which means the bigger equal to 8, and we'll try to run FA on J1, J2, J3. So we have J1, J2, J3 here, and so the end result should be 1 by square root 2 0 0 plus e to 2 pi 0.j31, and tensor e to 2 pi 0 plus e to 2 pi 0.j2j31, tensor 0 plus e to 2 pi 0.j1j2j31, and that's exactly those 3 qubits here. And so the last qubit, so this part, then this qubit should become 0 plus e to the 2 pi I, 0.j1, j2, j3, 1, and that's because this head mark give you 0.j1, and this control on j2 r1. Okay, I guess we have a different notation here. It's a bit annoying. So control on J2 here, and this R2 here. So this R2 here will give you this 0.0J2, and then control on third qubit, you get this 0.00J3 here, and then the second qubit. So I guess it's easier to use this. And then on second qubit, and the result will be this thing. This 0 plus e to the 2 pi 0 j2j3, 0.j2j3, because the hidden mark give you this j2, and this control on j3 give you j3, and finally on this circuit, and so that's erase. This is too much writing, and then let's see. On this point, and on this point you will get 0 plus e to 2 pi 0.j31, because that's just what the head mark do. And so you have those 3 qubits being those 3 states, and at the end you solve the first state and the last state, so you get the correct ordering of your quantum Fourier transform. Okay. And yeah, then finally let's do a little bit of counting. Okay, so how many gates we have in our QFT circuit? Okay, so we have order n squared control rotations plus the order n swap gate. Okay, and let's count a little bit more careful. And so we have so hidden mark control rotation. How many have? So we have n on first qubit and n minus 1 on second qubit, all the way to 1 on last qubit. So the total is 1 plus all the way to n, and so that's about order n squared. Okay, that's like n times n plus 1 over 2. That's order n squared control gate or hidden mark. And then at the end we have the swap gate. They are all in order n of them, because you want to swap all the ordering. Then you swap first one, last one, second one, last one, etc. Then order n swap, And anyway, in the end, you see you have all the small n gates here. And that's if you want to talk about big N, that's all the log square big N. Okay. And then let's go back to compare to when we do classical Fourier transform. And we don't talk too much about classical Fourier transform, so we just say that's fixed here. And so classical Fourier transform big N dimensional vector, you are basically trying to multiply big N by big N matrix. And so if you do it very slowly, so you just do it naive matrix multiplication, then you need to do about order n square multiplications. Okay, and but there are faster ways to do this, and in the end, you only do. But there are smarter way that's called phase Fourier transform, and you actually only need to do theta order n log n multiplication addition. But you can prove that this is the phase you can do. So you actually have big theta here. This is actually the phase you can do using classical computer when you try to do Fourier transform. Okay, and so you see that we are doing quantum Fourier transform is much faster than doing classical Fourier transform. Because classical Fourier transform you need basically order big N, but quantum Fourier transform you are exponentially faster. You only do order log square n. Okay. So quantum Fourier transform is much faster than classical discrete Fourier transform. But then you ask the question, can you use quantum computer to do Fourier transform exponentially faster? Then the answer is actually no. So you can do quantum Fourier transform, but quantum Fourier transform don't do classical Fourier transform. That's because remember we say quantum Fourier transform the input-output state quantum state, and but when you do classical Fourier transform, you want to get the output state as the classical vector, right? So I guess let's go to very beginning. Yeah. So if we do classical Fourier transform, basically you have the classical data of this vector. Then you want to get the classical data of this vector. So you want to know every component of this y. Okay. But if you have some, so suppose you have some quantum state encode this data, and then you do quantum Fourier transform very fastly, and then you get a vector of this data. But having this quantum state is not easy to learn all its coefficients, right? Because remember, yeah, so you kind of get this quantum state as the unknown quantum state. And remember we said that doing tomography is very expensive. Okay? So you actually need to do a lot of computation and even a lot of sample of those states to learn all the coefficients here. Okay? And even though you can do quantum Fourier transform really fast, it's actually hard to use quantum Fourier transform to do classical Fourier transform because you cannot read the data out of your transformed vector. Okay? And actually encode your data to an input vector is also a problem. But I think that's lesser of the two problems. Okay? And anyway, quantum Fourier transform has this input-output requirement being that they must be quantum state, and so it's a little bit of unwieldy to use. But I guess next week we are still going to see quantum Fourier transform allow us to do factoring efficiently. Okay, and yeah, so even though it doesn't do classical Fourier transform, you are still able to use it to do very useful quantum algorithm, and that's why I want to talk about quantum Fourier transform. Okay, and yeah. So I think that's finished about construction of quantum Fourier transform. So the people have question. Otherwise, I think we can let's stop early and come back in 10 minutes, and then next class we'll talk about phase estimation. Okay, yeah. So let's take a break now. Yeah. Let's see if this works. 吗？你说什么？
刚有申请听说。
哦哦。 Okay, guess let's get started, and we'll probably finish early today. Okay, and yeah, although we keep saying although we keep saying the application of quantum Fourier transform is factoring, but we are going to see something which seems a bit unrelated. I guess we are going to see factoring. We are going to build factoring from this seemingly different application of quantum Fourier transform. Okay, and so I should say quantum here. Okay, so the quantum Fourier transform, one of its application is this phase estimation. One of its application is this phase estimation precision. Okay. And what this phase estimation do is that we estimate the phase. So what kind of phase is this? Is that if you have some unitary operator, and it has you have some unitary operator and some eigenvector of it, and then because this thing is unitary, then we know its eigenvalue is going to be of the form of a phase e to a 2 pi I phi. Because the unitary operator cannot change the length of this eigenvector, so it can only give a phase to this eigenvector. Okay, and then the goal of phase estimation is exactly knowing this phase. So you want to know what is e to a 2 pi I phi, or because everything here is constant, equivalently it's asking what's this phi here. Okay. So yeah, so phase estimation is trying to learn this e to a 2, try to learn this phi for unitary operator and sign vector. Okay, and then we need to some kind of access to this unitary operator and this eigenvector, and so usually we'll assume that we can prepare the state U. This one is going to be changed a little bit, but for now let's assume we can prepare state U. And also we can do this unitary operator, but actually we need something stronger. So we need to do control version of this unitary operator, and not only control version, we need to do control a lot of this unitary operator efficiently. Okay, so we assume we can do control U to the j. So it's going to be a lot of these unitary operators, so this is going to be control U, control U squared, control U force, etc. And for now, let's say we can do all of them. We can do all of them efficiently. So control U squared, control U to the fourth, all the way to whatever. Maybe control U the input of phase estimation, and we see that. We're going to see that quantum Fourier transform allows us to do phase estimation really quickly. But for now, let's get some idea about doing phase estimation. So suppose we are in the easiest case to do phase estimation. So easiest case is that we have very low precision of phi. So we have phi being two extreme case. So phi is either 0 or 1/2. Because remember, phi is basically on a circle, right? So phase is a complex number. So maybe let's draw. Sorry, it's a spoiler. Maybe here. Okay. Remember, it's in phase. So phase is something on complex plane. So it's something from 0 to 2 pi, right? So phase is like you're asking you have some phase phi here. So your phase is some some Higgs number with phi here, and this number here is e to the 2 pi I phi. Okay, and so one of the most extreme case is that your phi is either equal to 0, so your either equal to 0, so your e to the 2 pi I phi equal to 0, or your phi equal to pi, and your e to the 2 pi I phi equal to -1. Okay, so you are distinguishing whether you have a 0 phase or -1 phase, or phi equal to 0 or 1 over 2. So I guess this angle here, to do standard notation, this is the angle here is actually 2 pi phi, because we are thinking about, so the angle is between 0 to 2 pi, and phi is like a fraction of 2 pi of your angle. Your angle is being phi fraction of 2 pi. Okay, so here you have a 2 pi phi angle, and you're asking what's its phase. Okay, and so your phi is 0, 1 over 2, then your eigenvalue is either 1 or -1. Okay, and if you want to find out whether your eigenvalue is 1 or -1, then let's go back to the technique we talked about in quantum algorithm, that is phase kickback. Okay, and so we find out that you can use phase kickback to distinguish whether your phi is 0 or 1 over 2. So and yeah, so this is what you do. So you prepare the plus state on your first register, and control this plus state. You have your eigenstate u here, and you have a control unitary here. Okay, so when we do phase kickback, we have a minus state here, but now we are trying to phase kickback this e to a 2 pi I phase. Okay, and so let's see what happens. So you have a control u 0 and control u on plus and u. And let's break the plus equal to the 0 part and 1 part. So plus is 1 over square root of 0 plus 1. So control u on 0u and 1u. And we see that control u on 0u, then obviously on 0u nothing should happen, because you are 0 on the control register, and the control operation should do nothing. So 0u is still 0u. But if you have control u on 1u, then so let's write this a bit more. So control u on 1u, then it should equal to 1, and you apply big U on small u, and this should equal to 1 and e to the 2 pi I phi, e to the 2 pi I phi on u, and because the phase is the location of phase doesn't matter, so you can put this phi key. So your phase keep is e to the 2 pi I phi on 1, and you see the second register still stays u, because the eigenvector of big U. And yeah, so you see that this 1u become e to the 2 pi I phi 1u, and then you take out this u tensor product u on both 0u and 1u, so, and then you're left with 1 over square root of 0 plus e to the 2 pi I phi 1u. Okay, and then just like our phase kickback, just like our phase kickback algorithm before, and this e to the 2 pi is equal either 1 or -1, and so depending on your phi is 0 or 1 over 2, then you get a plus state or a minus state here. And so you see that if you have so if you put the extra hedema, so you put the hedema and the measurement like before, like in our George's algorithm. So if you put the extra hedema and the measurement here, then you can distinguish whether your phase is 0 or 1 over 2. If it's 0, then your hedema measurement result will be 0, because the plus turns into 0 and get measured. And if it's 1 over 2, then it's minus 10 into 1 by hedema, and you measure, you get 1. Okay. And yeah, so you see that you can perfectly distinguish this phi equal to 0 or 1 over 2 using this circuit. You have a plus state as input, and to control unit on it with the second register, start with your eigenvector u, and yeah, you get this end result be either plus state or minus state on the first register, and then you can perfectly distinguish them. Okay, so that's the easy case of phase estimation. People have question, and it's easy to see there's a drawback of this algorithm that it only estimates 1 bit of psi. Overall, we only do 1 bit measurement. And so this kind of only works when psi is 0.j1. Psi is in this form of 0.j1. And I guess we adapt this Wikipedia notation or break it. Okay? Break it means that it's binary. Okay? So phi is, if phi is 0.j1, then we can use this phase estimation algorithm, this kickback phase estimation algorithm. And let's do it in general. So if our phi is, a typo here. Okay, so phi is heavy more bits. So phi is 0.j1, j2 to jn. So assume phi is still some binary fraction, but it now has many bits. Okay, so phi is some 0.j1, j2 to jn. And how we do phase estimation is kind of a similar idea. So we do phase kickback with more bits. Okay, so we now do assume let's do t bits, and for now we'll have t equal to n. Okay, because it's easier with t equal to n. So now it's a bit funny. Okay, and so we have t equal to n bits, q bits here. That's going to take the kickback phase. Okay. And each one of them is initialized to a plus state, so kind of like this. So you have start with 0 and do hit mass, so each one of them is plus state. And then you phase kickback with different order of u. Okay, and so you have u to the 2 to a 0, and 2 to a 0 is equal to 1, so it's just u to the 1. And then you have u to the 2, then you have u to the 5 to u to the 2 to the t minus 1. Okay, and it's a control on the first key, the last key. Then there are control on first bit. So I guess it start from control on last qubit, and second last qubit, third last qubit, all the way to control on first qubit. And then you see that it's similar to the. Oh, why is this weird? Okay, not sure why the picture here is bad, but we are missing a whole bunch of plus sign here. And we claim that the end result is that you have this 0 plus some phase of 1. Okay, and I guess it's kind of obvious. So because each qubit is basically what they do is independent of each other. Because after you apply each control unitary, the last qubits just stay u. This second register just stay u all the time, because this is some part of u, but any part of u, this small u is still eigenvector. So the last register is going to stay u, and you will provide different amount of phase kickback to the previous qubits. Okay, and let's see for different qubits. So say for the last one is control on u to the 1. So this thing is u to the 1. And it's exactly same as the previous circuit. Okay, so this thing, we say with phase kickback, we will get e to the 2 pi phi here. Okay, so you get e to the 2 pi phi here on the last qubit. And on the second last qubit, you do u twice. So you keep e to the 2 pi 2 to the 1 phase, and you can see similar thing going. And third qubit or second last qubit, you do u to the 2 to the 2, and so you just apply u to the 2 times, so you get 2 to the 2 times of the phase getting kickback, 2 to the t minus 1 times phi here. Okay, so each one of them is just power of u. So small u is all eigenvalue is always small u is always an eigenvector of those control unitary, and with a different amount of phase getting kickback. And so you do whatever amount of exponentiating of this u, then you get the corresponding amount of phase here. Okay, and so final state is this. See that once again we have this yeah. Once again we have this excuse me familiar expression of 0 plus some phase on one tensor with 0 plus some. The integer part, as we said before, it doesn't matter because e to 2 pi k equals 1 for any integer k. And so the first register you just left with 0.jt. And the second register you are left with 0.jt minus 1 jt because you only multiply 2 to the t minus 2. And all the way to the last one is just 5, so that's 0.j1 to jt. And as we said, this is the same as the Fourier transform of something, and that something is Fourier transform of j1 to jn. Okay. Yeah. So this is a Fourier transform of this thing being j1 to jn in binary. And that's just 2 to the n times j times UFI. Okay, and I guess I should yeah, and it's a bit annoying, but let's keep the notation of t equal to n here. Yeah, and so that's j1 to jn, and so that's yeah, so that's the Fourier transform of j1 to jn. And if you write down Fourier transform is also equal to this thing. And I guess we don't really need this. We only need to know that the Fourier transform of j1 to jn. And so if we want to learn j1 to jn, all we need to do is we apply the inverse Fourier transform. So we just run the Fourier transform circuit backward, and we'll get the state not phi, 2 to the t, we'll get a state that's 2 to the t times phi. 2 to the, I guess here is make more sense to say n, but anyway, 2 to the t times phi. Okay, and yeah, so that's exactly how our phase estimation circuit works. So you have TQB here, and you have some amount of QB here. So I guess here we should really, so small typo. So here maybe I should have some n prime. So this n is yeah, because we use n as jn, j1 to jn. Sorry, let me try to fix the notation. So maybe it's easier here if I make this jt here, so that's less confusing. So assume our bits are j1 to jt. Okay, so then we don't need this t equal to n here thing here. So our things are just j1 to jt, j1 to jt. j1 to jt, and this is j1 to jt. Excuse me. Sorry for the confusion. So assume our phase is something j1 to jt, and some 0.j1 to jt, and then we use TQB to do this phase estimation, and we see that if we run this circuit, this huge phase feedback circuit, and we run inverse Fourier transform, then we get 2 to the t phi, and then that will actually get all bits of phi, because then you do measurement at the end, then you will get each QB is going to give you j1, j2 all the way to jt. So you can get every bit of this phi exactly, and that's how you do phase estimation. And here is a schematic of our phase estimation circuit. So we say that So I guess the only different part is we write down the middle part in a more complex form. So I guess we kind of consolidate the first t qubits. So we say start with 0 to a t, and then we do Hedema to a t here. And then instead of doing this, saying that you have separate control on each instead of saying you have this separate control on each qubit, we say what we do is we control on first qubit being some k, then apply u to the k. And so here we have we do the so here we do the mapping between 0, 1 to the n, and 0, 1 to the n to number from 0, 1 to 0, 1 to a small n to 0, 1 to big N minus 1. Okay, so I identify the bit string here to okay. So this big K here, this small k here is some number between 0 to n minus 1. Between 0 to n minus 1, that's determined by the bit string here. But anyway, you can convince yourself that the thing we did here before was actually control u to the k. It's not very hard because this is basically a binary representation of the bit string. So you see you have the first qubit times 2 to the t minus 1, and second qubit times 2 to the t minus 2, over to the last qubit times 2 to the 0. So the number of times you apply is actually just the binary number represented by all the qubits here. Okay, and so that's only something extra here. Anyway, so that's the circuit we run. We put the eigenstate u on the second register, and first register as 0 to the t goes through Hedema to the t, so it's a uniform superposition of all the bit string here. And then you apply this control u to the k here, and so the space key bank should give you e to the 2 by k phi times and then the first qubit was summation over k, and the first register was summation over k, and the second register was is always u. Okay, and here you see this is a more straightforward expression of why this is why the circuit was the Fourier transform, because this is exactly on the first qubit. This is exactly the Fourier transform of phi. Okay, so if you have the state, this was a Fourier transform of phi times 2 to the t. Okay, and yeah, and then you see that after you apply inverse Fourier transform, then you are just going to get this j, that's phi times 2 to the t. Okay, so if phi is on j divided by 2 to the t, then you see that this expression here is summation k e to the 2 pi jk over n, and then that's just exactly just the Fourier transform of j. So you apply inverse Fourier transform, will learn j, and j equal to phi times 2 to the t, and obviously you learn j, then you know phi. Okay, and small caveat here is that if you want to do this efficiently, as we see, you need to a small caveat here is you need to do a whole bunch of control u. You need to do control u to some very large number, potentially 2 to the t, and you want to do all of those efficiently. So you want to do u to the 2 to the t efficiently. Okay, that's an issue we need to deal with when we do factoring. Okay, and so that's the phase estimation. And then we just have 2 more slides, and I think we will quickly today. So first thing is that one of the requirements we can get rid of in phase estimation is we keep saying we need like a eigenvector here, u here, and actually sometimes even if you don't have the eigenvector u here, you can still estimate some phase of your unitary big U. Okay, that is, you can just pick a random state. So some random state equal to summation u a u sub u means that so those small u are once again different eigenvectors of your big U. Okay, so we think the eigenvectors of big U is some set small u. Okay, and it's a orthonormal set, so you can express any vector as a linear combination of the eigenvectors of U. Okay, so this set of U is eigenvectors of big U. Okay, and so you pick a random state, and then you just put this random state on your second register, and you do phase estimation. And you know that, and then you know that because 0u is going to give you because we know that our phase estimation should do 0u. Excuse me. Phase estimation do this thing. 0u doing phase estimation become phi sub u, and then phase estimation is, well, it's a quantum operation, it's linear. So if you have a linear combination of different 0u, then you just get a linear combination of different psi u as output. Okay, and so then if you measure and so if you measure the result, so if you have this random input state on the second register, and you run phase estimation, you are just going to have this superposition of different eigenvector u and different phase psi u here. And so if you just measure the first register and the end, you are going to get different psi u, and with different probability that just correspond to amplitude square here. Okay, and yeah, so you can get random eigenvalue. You can get random phase or random eigenvalue by having a random starting state here. Okay, so that's some getting around the requirement, and I guess then more important slide is this. This is a bit of is about accuracy of phase estimation, and so the textbook has detailed calculation, but we'll be short on time, so we'll just skip on it. And also, yeah, and so the issue here is that we assume our we assume our psi. I guess we had t there, so let's have t here. Okay, so we assume our psi was exactly some binary fraction, 0.j1, j2 to jt. Okay, but not every number can be written this way. In particular, your phi might be some irrational number. Maybe I guess you cannot be square root 2. Oh, sorry. Phi might be say phi might be 1 over square root 2. So we want something between 0 and 1. That's nicer. Okay. So maybe phi is an irrational fraction, is 1 over square root 2, and you can never be expressed as this fraction 0.j1, j2 to jt. Okay, and so what happens when our phi is not exactly in this form, and we want to do phase estimation, and then we run into accuracy issues. So, and in that case, so there are basically two analyses we can do. So first is let's ask us what if we want to estimate the phi to some accuracy to the method. So we want to, so phi is maybe irrational number having even number of bits, but we want to learn the first n bits of it. So with accuracy to the method, we have NB precision, and then we find out that we cannot do that exactly, but we can do it with pretty good probability. So we want the probability of success being 1 minus epsilon, and if we want to do that, then So we still run this circuit. And if you analyze it carefully, you find out that you can get MB accuracy and error less than epsilon with not too much effort. You just need to have T bits. That's basically the accuracy plus log 1 over epsilon. And the exact number is the scaling of log 2 plus 1 over 2 epsilon. But being lazy is order log 1 over epsilon bits. Order log 1 over epsilon here. Okay? So basically, if you want the MB accuracy, then you need you just need to run this circuit with n qubit here with a little extra for if you want a smaller error epsilon. Okay, and so T is the number as we had before. T is the number of qubit in the first register of the phase estimation. Okay, and so this thing has we have a detailed calculation in a textbook, basically saying that the error decays as a quadratic decay as a 1 over some L squared. But anyway, so you can find the old lectional textbook for the calculation. And so that says phase estimation has very good accuracy. And another good thing about accuracy is that so this thing is for you want arbitrary small epsilon error probability. And if you just want to have a kind of a good probability, then you find out that if you just do this thing, then you have a pretty good probability that you just get the first TP correct. Okay, so you just have a TQB here, then the probability of getting the first TP correct means that the error here is less than 1 over 2 to the t plus 1. Is at least is 4 over pi squared equal to 0.405. So if you just do this on any phase, then with 40% probability you will get the first TP correct, and that's actually already good enough for doing factoring. But anyway, year one result is good enough analysis for us. And so the proofs are a bit more details. We'll make a proof here and just say that you can get about TB of accuracy by having TB in your first register of your phase in the first register of your phase estimation. Okay. And and if you want to see more detailed results, you can look up the proofs. Okay, any question? Otherwise, I think that's the end of slide today, and I think we'll just end the class early today. And next time we will start talking about factoring. Okay, so see you on next Tuesday.